Welcome to Lesson 15b, particle settling in moving air. Last time we looked at particles settling in quiescent air. Now we're going to look at particles settling in moving air, and then we'll compare laminar and turbulent settling. Before we start, I want to quickly review our approximations. We're considering a monodisperse aerosol, so we can analyze one particle at a time. But we can repeat this for a range of particle diameters. And so whatever analysis we do here applies to polydisperse aerosols as well, because we're assuming that these particles are far enough apart they don't interact with each other. So we're really treating one particle at a time and then extending it to any distribution of particles that we have. Quick review. For quiescent air, which means still air, for a coordinate system with x to the right, z up, and gravity down, which is what we'll always use here. Suppose we have a particle, and at time t equals 0, it has some initial velocity that's just shooting off in some arbitrary direction. What will happen is it'll very quickly start to fall vertically, and then eventually it will settle at some terminal settling speed vt. This part of the trajectory is very fast. We can typically ignore it, and we just approximate that as soon as this particle starts existing, whether it's shooting off in one direction or another, it's just going to start falling at speed vt. In other words, looking from far away, we just ignore this part here. Now let's add wind. I'm going to assume the wind is blowing in the x direction. So u vector is just u magnitude times I, where I is the unit vector in the x direction. So we're talking about a uniform wind, which looks something like this, just a nice steady wind to the right. Now let's consider this same particle. It starts at some v0, and now what will happen is its trajectory will look something like this. We're after some short time where it kind of adjusts itself. Again, this time is very short, this part of the trajectory. If we take it at some later time, this particle will still be falling at vt, but it will also be moving at capital U to the right. So the resultant is just the vector sum of these two, complete the parallelogram. And so our little v is that vector there. It's just a superposition of capital U to the right and vt down. You can also imagine yourself as a camera moving with the wind. What I'm showing here is from an absolute reference frame, but if you were moving with the wind, you would see this. You would just see the particle falling. So again, we ignore this green part here and just assume that as soon as the particle starts existing, it's going to start moving down and to the right. And at any point along this trajectory, it's moving at vt down and it's moving at capital U to the right. So if we have laminar wind, in other words, this wind is very smooth, it's just not fluctuating at all, it's just nice and uniform and steady. The bottom line is that our general terminal settling speed equation that we derived previously is still valid, this equation for vt, the one that we have to iterate with. We still get the same vt as before, but we just add a capital U vectorially, and that's all there is to it. Now, what if the wind is turbulent? For turbulent flow, we still have capital U as the average wind speed, but there's going to be a lot of fluctuations with this wind because it's turbulent. So in a turbulent flow, there's all these eddies, some big ones, some little ones that are moving around. But on average, the wind is moving to the right at speed U. But there's going to be some vertical components and some components in and out of the page, even it's three-dimensional with the turbulence. But think about a particle that's being moved along in this wind. This particle is still going to have a tug on it by gravity, and it's still going to want to fall at vt. But in addition, it'll be swept up into some of these vortices and be kind of moving randomly around. So let's compare the laminar case and the turbulent case with the same mean u. Well, the laminar case, we know that it's just going to fall at vt, as we just described, and it's going to move at capital U, and so it has an overall net v that's just down and to the right. For the turbulent flow, what's going to happen? Well, it's going to get caught up in some of these eddies, so its trajectory may look something like this, all kind of messed up. But the important thing is that on average, it's still going to move at speed u to the right, because that's what the wind is doing. And on average, it's still going to fall at speed vt due to gravity. So for a long time average, the particle is still falling at vt, and it's still moving to the right at u. And it still has the same v as it had in the laminar case. It's just going through a more circuitous path to get there. Everything's unsteady, but if we take a long time average, we still see that particle falling at vt and moving at speed u to the right. For both cases then, horizontal speed is u. For laminar flow, it's just u, which is a constant. For turbulent flow, we would just say on average, and that's to the right. Vertical speed is vt on average down. So in our calculations, there's really no difference. I just wanted to mention, let's suppose there's some eddy in a turbulent flow like this, and you have a particle. Very small particles will move along with the eddy. Bigger, heavier particles will have some inertial separation, so they'll move like that. We'll talk about inertial separation later. If the eddy's that way, the big particles will tend to move out like this when there's no gravity. When there's gravity, there's also this tug that's always on these particles trying to move them down. So this would be the no gravity case. If we add gravity, the particle's still going to have inertial separation, but it's also going to be slowly moving down compared to the air because of this VT. So this would be with gravity. The same case here, it'll tend to start moving down. So what I'm trying to say is that even though the particle is moving up and down and swirling around with all these eddies, it's doing that, but all at the same time, it still has this VT that's constantly pulling it down. And in the long time average, you end up with the same result as you had for the laminar case up here. So the bottom line is our general terminal settling speed equation here is still valid on average, and it's superimposed vectorially as a vertical component added to the horizontal wind velocity. So we really treat laminar and turbulent the same way on average. Let's do a quick example. We have a particle settling in a uniform wind. Spherical particle starts at an elevation of 200 meters. The wind is given 2.65 meters per second. And we have the pressure, temperature, dP and rho p. And what we want to do is for laminar wind, calculate how long it takes for the particle to hit the ground, and then repeat for turbulent wind at the same average wind speed. Well, first of all, we notice that this is not SATP, so we have to calculate the air properties. You know how to do this. Make sure you can get these numbers from previous lessons, and I gave you all those equations. I get rho is 1.1503 kilogram per meter cubed. Mu is 1.837 times 10 to the minus 5 kilogram per meter second. And mean free path lambda is 0.06885 micrometers. I'll put here in red, make sure you can duplicate my results. As I have been saying all along, you should have all this already programmed in software. Just plug in a given P and a given T and you should be able to generate these. Likewise, for those plus a given particle diameter and density, you should be able to plug into your software for solving for VT. So that's all review. Make sure you get this. VT is 0.02036 meters per second. By the way, if any of you are having trouble programming this, you need to talk to me because, as I promised, you keep using this over and over again, and we're not done yet. Well, the rest is simple physics from middle school physics class using the distance speed time relationship, namely delta Z is VT times delta T. We solve for delta T, which is what we want. Delta T is delta Z over VT. Now, what I'm doing is talking about a particle that's initially at some delta Z elevation. Z's from the ground. Now it's actually falling in a path like this, a straight line that, as we've drawn many times now, has a component in the horizontal direction U and a component in the vertical direction VT. So that's the path of the particle, but we can separate out the X and the Z directions. So the particle is essentially just falling at VT to the ground. It's also moving to the right. It'll eventually hit the ground at some distance X to the right here, but I didn't ask for that. All I asked for was how long it takes for it to hit the ground. So for the laminar case, everything is nice and uniform. We plug in our numbers. The initial height or elevation was given as 200 meters, and then the VT we just calculated is 0.02036 meters per second. I need 2 unit conversions here, 1 minute per 60 seconds. I forgot to type this in. I want this answer in hours. So I have to convert to hours. 1 hour is 60 minutes, and I get 2.73 hours, which is my answer for the laminar case. For the turbulent case, it's doing something like this, not to scale, but it eventually hits the ground. It's the same delta Z to start with. We use the same equation because on average, this thing is just moving at that same speed and direction as the laminar case.
But what if a strong eddy slams the particle to the ground? Wouldn't that make delta T smaller?
Yes, it would, Arnold. So this delta T is not as accurate as the laminar one.
Okay, thanks.
So for part B, I'll give the same answer, except I'll say approximately 2.73 hours. It's approximate because when you get down close to the ground, depending on where these eddies are, so if you have an eddy that happens to slam it to the ground a little earlier, or if you have an eddy that sweeps it up right before it's ready to hit the ground, it may last a little longer. So that delta T will vary a little bit, probably in the 3rd or 4th digit, but I'm not worried about that. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.